In this video, we will talk about definite integral properties. So the first property says that if we have the integral from a to b of f of x dx, that is equal to the negative integral where we switch these numbers, so the b down here and the a up here, f of x dx. Okay, and the reason for this is that if we think about what delta x would be if we were to evaluate the definite integral on the left-hand side using a limit of Riemann sums, delta x for, I'm going to write LHS. And LHS just means the left-hand side of that equation. Well, that would be, so it's the length of the interval, which is b minus a, divided by n for the number of rectangles, but the delta x for the right-hand side, which I'll call RHS, for the right-hand side of this property, would be a minus b over n, which are opposites. So these are opposites, and that's what contributes to the fact that we have this negative sign. Alrighty, so property 2 says if I have the integral from a to a f of x dx, well, if I was doing that, then if I had a graph of a function, I would just be looking at, well, what's going on from a to itself, and there would be no area there, so this is just going to be 0. So this is going to be 0 because there is no area here. So property 3 talks about if I have the definite integral from a to b of a constant function c dx. So I want to motivate the reason for this with a picture. So I'm going to draw some axes. So I'll draw some axes and I'll have my interval from a to b. And I want to draw the graph of a constant function. So that is a horizontal line. So this is a horizontal line through y equals c. So we are focusing on the interval from a to b. And the definite integral represents this area, the area underneath this curve over that interval. And by looking at this picture, this is just a rectangle. So I can find the area of this easily. The area of that rectangle is just going to be, well, the length of that base, which is b minus a, times the height, which is c. And that's the value of this integral. It's going to be c times b minus a. Alrighty, we are on to property 4. Property 4 is, what if I have the definite integral from a to b of a function plus or minus some other function? Well, this is, I think, what we'd kind of expect to happen. We can split this up into pieces as the integral from a to b of the first function dx, and then either plus or minus, depending on what this sign was, the integral from a to b of g of x dx. Property 5 is really similar. If I have a constant c multiplying my function, we can pull that constant to the front, and then that'll multiply my integral from a to b of my function f of x, and then I write that dx. Okay, so property 6 now is going to be a little bit more interesting. It says that if I have the integral from a to c of my function plus the integral from c to b of my function, before I say what this is, I want to draw a picture to help motivate it. So I want to talk about the reason. So let's draw a picture. So let's draw some axes, and I'll draw some function. All right, and I'll draw a here, and then c, and then b a little bit further. Okay, and so my first integral is from a to c, so I'm going to shade that area in. From a to c, that would be something like this. My second integral is from c to b, so let's shade that in a different color. C to b, that would be something like this. That would be all of this area. So if we were to add up those two areas together, that just gives us the whole area from a to b. So I can express that as one integral from a to b f of x dx. And in this picture here, the value of c that we had was in between a and b, but it turns out this will still be true if c is not, even if c is not between a and b. And actually, if c wasn't in between a and b, I could still draw a picture of this and explain it visually, and I could justify it using alongside property 1. Okay, so property 1 is a little bit weird because we might, when we see this, think, if I had the integral from a to b, why would I want to write it with those numbers flipped and put the a on top and the b on the bottom? One of the reasons why this helps is in showing something like property 6, even in the situation where c is not between a and b. All right, let's look at an example. Okay, so in this example, it says to suppose the integral from 2 to 8 of f of x dx is 12, the integral from 21 to 30 is 15, and the integral from 2 to 30 is 6. We want to evaluate the integral from 21 to 8 of f of x plus 2. Okay, so the first thing that I want to mention is these numbers that we write at the top and at the bottom of an integral, these are called the limits of integration. Okay, so I'm going to introduce that terminology because I'll talk about these for the rest of the course. Okay, so in our problem, because this upper limit of integration is smaller than that bottom one, I'm going to flip this integral and do 8 to 21. And when I do that, I got to stick a negative in front of it. And then I have my function f of x plus 2 dx. Now let's split up this integral into two pieces. So I got that negative sign in front, and then of the integral from 8 to 21 of f of x dx, and then plus the integral from 8 to 21 of 2 dx. All right, so let's handle these integrals one at a time. So if I start with this second integral, I know that I have this constant function here, and we've handled constant functions in one of our properties, but let's just remind ourselves of the picture. So my interval is from 8 to 21, and if I draw the function y equals 2, we get a horizontal line. So a horizontal line at y equals 2, and we want the area in between 8 and 21 here. So if I shade that in, that forms this rectangle. Okay, so the area of that rectangle is going to be, well, the height is 2, and the base is 21 minus 8. So this is 2 times 13, and that's going to be 26. All right, so let's do the other integral in here now. So we have this integral from 8 to 21 of the function f of x. So for this, I'm going to draw a picture. I'm going to draw some axes. And then I'm going to draw the graph of some arbitrary function because I don't know what f of x looks like. So I'm just going to draw some curve. All right, and then I'm going to put a tick mark at every number that showed up as one of the limits of integration in the original problem. So I'm going to put tick marks at numbers like 2 and 8 and 21 and 30. So let's see, I would have 2, 8, 21 is a little bit further, and then 30 is a little bit further. Okay, so I'm going to draw some horizontal lines, vertical lines at these numbers. Okay, and if I look at what the problem told me, I'm given that the integral from 2 to 8 is going to be 12, and then from 21 to 30 is going to be 15. So in our picture, from 2 to 8, I know that this area is going to be 12. And from 21 to 30, I know that area is going to be 15. And this last integral says the area from 2 to 30 should be 6. So this whole area from 2 to 30 should be 6. And if you're looking at this and thinking, wait, that's weird, because that's 12 and that's 15, those already add up to 27, and that's way more than 6. So that's absolutely valid. But what that means is probably the graph, it didn't quite look like this. The portion between 8 and 21 probably went below the x-axis to give us a negative area. So it could add up to 6. Okay, so how do I find what that middle region is? So I'm going to do this rigorously.
Sorry, I don't know that.
So if I take the integral from 2 to 8 of our function, and then I add that to the integral from 8 to 21 of our function, and add that to the integral from 21 to 30 of our function, essentially I'm going to add up these three areas. And when I do that, that'll give me the whole, it'll give me one integral from 2 to 30. And I know what a bunch of these are. I know this first integral is 12. I know this third integral is 15. And then in the middle, we'll have plus the integral we want from 8 to 21 of f of x dx. And then a plus sign here. And that equals this last integral, which we know is 6. Okay, so if we subtract the 12 and the 15, we'll get the integral from 8 to 21 of f of x dx is 6 minus 27. That's going to be negative 21. All right, so if I put this together, what we end up with is we have this negative sign in front. And then this first integral we just got was negative 21. And then that second integral, well, we had done that one first. That was plus 26. Okay, and working this out, this will give us negative 5, and that's our answer. All right, so we are ready to state a few more properties. So the comparison properties say that if for all values of x in the interval from a to b, if my function f of x is greater than or equal to 0, then when we do the integral of that from a to b, that integral should be greater than or equal to 0. Because graphically what this is saying is on this whole interval from a to b, our function is greater than or equal to 0. It never goes below the x-axis. So it makes sense that our area should be non-negative. Okay, the second portion says if for all values of x on that interval from a to b, f of x is greater than or equal to g of x, then the integral from a to b of f of x should be greater than or equal to the integral from a to b of g of x. So conceptually, because the graph of f of x, let me draw a picture. If I have my interval from a to b, so the graph of f of x is the higher one than the graph of g of x. So g of x could be less than this or maybe equal to, maybe it's equal to at a couple of points. It's never going to be greater than it, greater than f of x on this interval. So that's happening, then the area under that f of x graph is going to be greater than or equal to the area under that g of x graph. That's what the second portion says. Alrighty, so let's look at an example. So in this example, I want to show this chain of inequalities, and I'm going to do this using these comparison properties. Okay, so the way I get this started is I say the variable that x is in. Sorry, I say the interval x is in. And x is in between negative 2 and 1 based off of my integral here. And then I'm going to start to do the same thing to each part of this chain of inequalities to make the middle eventually look like the function I am integrating. Okay, so I need to now look at x squared and what that is going to be in between. So I'm going to do this using a graph. So if I look at the graph of y equals x squared, I could also just do it using a little bit of logic and just think about, if x is in this interval, what would x squared be in between? But I'm going to use the graph just to be careful. So my interval is from negative 2 to 1. And when x is negative 2, the y value is 4. When x is 1, the y value is 1. So we are just limited to this portion of the parabola. And on that portion of it, the smallest the y value ever gets is here at the origin, and that y value is 0. That's the smallest x squared ever gets. And the biggest the y value ever gets is here, and that y value is 4. Okay, so I got what x squared is in between. All right, so now I need this e. So I can just take e to everything, and that'll preserve these inequalities. So I'll get e to the 0 is less than or equal to e to the x squared is less than or equal to e to the, this should be e to the 4th. And e to the 0 is 1. Okay, so the next thing let's do is add 1 to everything. So e to the x squared, I'll leave myself a little bit of room, e to the 4th. And then this is 1. So I'm going to add 1 to everything, plus 1 here, plus 1 here. Okay, now I need to reciprocal this. So when I reciprocal the middle, 1 over e to the x squared plus 1, because everything in this chain of inequalities is positive, that'll flip my inequality signs, and then I'll reciprocal these other pieces. So this first part is going to be 1/2, and this last part is going to be 1 over e to the 4th plus 1. Now the middle of this chain looks like my function, this integral. So by the comparison properties, if f of x is greater than or equal to g of x, when I take integrals of both of those functions, that inequality stays the same. So that's what I'm going to do next. Take the integral of everything here. So we'll do the integral of this one from negative 2 to 1, and the integral of this one, and the integral of the last one. So of our function, 1/2 And then this one is going to be 1 over e to the x squared plus 1 dx. Notice I'm keeping these inequality signs preserved. Okay, and this is 1 over e to the 4th plus 1 dx. So we got to do the integrals of these outside pieces. But I noticed that the 1/2 and the 1 over e to the 4th plus 1, neither of those has an x in it. So they are both constants. And we've seen how to do a definite integral of a constant a couple of times in this video already. What we get is just that constant, which in this case is 1/2, multiplied by the length of the interval, which would be 1 minus -2, which is 3. Okay, and then this is greater than or equal to my middle integral from -2 to 1 of 1 over e to the x squared plus 1 dx. And that's greater than or equal to this constant, 1 over e to the 4th plus 1, and then times the length of this interval, which is also 3. Okay, and if I look at what we have, this is the chain of inequalities I was hoping to prove. I've just written it in the reverse direction with the inequality symbols flipped. But at this point, we have proved this result. I'll put a check mark here. So forming inequalities like this, they can be helpful when I have an integral that I can't figure out. In the next section, we'll talk about a way to evaluate definite integrals using antiderivatives. But sometimes there'll be functions I can't even find the antiderivatives of. And in those situations, it may be helpful to try to estimate the value of the integral. And that's what we've been able to do using this comparison property.